Okay, I just wanted to make a remark then about the assignment. So the data that we looked at today, which went out to Hubble data, went out to what we call Z's, the fractional redshifts, close to 1, were data that first came about in 1998 from several groups working to use, rather than, we mentioned these Cepheid variables, these pulsating stars that we use as standard candles by Hubble. Nowadays, also, type 1a supernovas are used as standard candles. Now, the difference is that the exploding stars are much brighter than the pulsating stars. Because they're much brighter than the pulsating stars, you can see much earlier back in the universe than you could with using the pulsating stars for standard candles. And so that opened this new window to look at the expansion way back in time. And so what came out of that was this big discovery. The leaders of these groups got the 2000-something Nobel Prize for this. That not only is the universe expanding, but the rate at which the universe is expanding is accelerating. And so that was a huge discovery. Actually, it was thought that if you were to look at the rate of the expansion, you would actually see it decelerating because of the gravitational attraction between galaxies, for example. But actually it seemed to be accelerating rather than decelerating. So it's a huge discovery. And I'm sure you've heard of dark energy as one, probably the most common idea for why there is an acceleration, why the expansion is accelerating. Dark energy is probably the most common explanation of the accelerating expansion of the universe. Is sort of based on this idea that in the vacuum is not empty. It's not just completely empty. In the vacuum, there are particles and antiparticles being continuously created and destroyed, sort of in accord with, like, the Heisenberg uncertainty principle, or in accord with, more quantitatively, quantum field theory. So we think of the vacuum as not being just empty space, but rather having this sort of sea in it of particles and antiparticles being created and destroyed. So electrons and positrons being created and destroyed. Quarks and antiquarks being created and destroyed. So all this is going on in the vacuum. And all that contributes to an energy of the vacuum. And you could imagine that vacuum energy could drive this, accelerate this expansion. The problem with that idea is that, so you can calculate the vacuum energy based on the known particles and forces of nature. So you can do that calculation, and then you could compare it with what is being observed for the expansion of the universe. It's interpreted as a vacuum energy. So you can compare those two things, like you've observed it through these cosmological observations, and then you can calculate it, get a particle physicist to calculate it. And here's the problem: it's off by like somewhere between 10 to the power 60 and 10 to the power 120. So the theoretical estimate, it's the greatest sort of theoretical disaster. The calculation is off by this enormous numbers of powers. And so whilst it remains kind of the common explanation, there's no calculation of what this dark energy content should be. It is really, it's calculated to be 10 to the, at least 10 to the 60 times larger than it's measured to be.